Imagine you are in a bar with 5 friends and each of you earn, let's say, about 85,000 a year, and suddenly Elon Musk walks in. Technically, the average annual income of people in the room just skyrocketed to something like $100 million. Yet no one in the room is a penny richer. So what happened here? This is an example of an ambiguous average, a statistical plot twist where the numbers can tell a legal truth while telling a total lie. So to understand what's actually happening, we need to understand 4 statistical tools that are used to turn a heap of numbers into reliable summaries. The average or mean, the median, the level-headed middle value of your data that isn't distorted by a billionaire walking into the bar, the root mean square or RMS, the mathematical way to measure the typical magnitude of numbers, and the standard deviation or sigma. It's the measure of spread of your data around the average. This is what we talk about in this episode. Here is another example. Each month, the Office of Labor Statistics calculates average hourly earnings from the payroll data that companies provide to them, right? They figure the total wages paid out, then divide that by total hours worked to work out the average. And what's become evident, they see that during the recessions, the average hourly earnings goes up. And when the recession ends, the average hourly earnings starts going down. How is that possible? In the last episode, we talked about the histograms, which is a graphical tool used to summarize large amounts of data. And often we need to deal with an even more condensed summary of the data, just the center of the histogram and the spread around the center. So, for example, look at these 2 histograms, which are shown here in this picture. These histograms can be summarized by the center and the spread. Okay, the center and the spread are also marked on the histograms. You can see that both of the histograms have the same center of the data, which is 50 in this case. But the second one, the one on the right, more spread out. There are more area further away from the center. And also note that when we say the spread is larger for the one on the right, this is why the range of both histograms, both data sets, it's between 0 and 100. Okay, so it's not about the range, it's about how data are basically spread around the average. On the second one on the right, there is more area further away from the center, and that's why the spread, we say, is larger, even though the range for both histograms are the same. For statistical analysis, we need more precise definitions. Okay, so there are several ways to do this, to describe the center and the spread of a data set. The average often used to find the center. Also, we have another parameter in statistics, which is the median. And the standard deviation is used as a measure of spread around the average. There is also another measure, another tool that we use to measure or to talk about the spread of data, and it is the interquartile range. Okay, note that not all the histograms can be summarized by the center and the spread. For example, in this figure here, you can see the distribution of the elevations over the Earth's surface, and the area under histogram between 2 elevations basically gives you the percentage of Earth's surface area between those elevations. If you take any 2 points and measure the area under the histogram between 2 elevations, elevations are on the horizontal axis, and when you measure the area of the histogram between these two elevations, it gives you the percentage of the Earth's surface area between these two elevations. And obviously you can also see two clear peaks in this histogram. And what is this histogram is telling us is that most of the surface area is occupied by the seafloors, which is about 2 miles below the sea level, or it's the continental land around the sea level. So that's the second peak. Okay, and the problem is that if you want to report only the center and the spread of this histogram, okay, then the two peaks would be missed by reporting only on the center and the spread. So that's why you should pay attention also that not all histograms can be summarized by center and the spread. So let's look at the average. The average of a bunch of numbers, we say, is their sum divided by how many they are. Actually, that's how we calculate the average of a bunch of numbers. Okay, we take their sum, we sum them up, and then we divide by how many actually they are. It's a simple but powerful tool to summarize data. But the problem is that, as we saw with the case of your salary in the bar, and then someone super rich comes into the bar, the problem is that it smoothes away the individual differences. Let's look at this simple example of these 5 numbers, 5 entries, 9, 1, 2, 2, 1. What is the average? You basically sum them up. 9 plus 1 is 10. You add another 2, then another 2, it's 14, and then 1, which is 15. So that's the sum of the entries, and then you divide by the number of the entities, which is 5. Yeah, 9, 1, 2, 2. There are 5 numbers, so 15 divided by 5, you have the average 3. So another example, look at the average height of men in a certain age group in your office. Okay, so you measure the height of all the men in your office which are within a certain age, and then you get the average height as to be 178 centimeters. But you will realize by looking closely at the data that 10% of them were taller than 188, and 10% were shorter than 160 centimeter. So this diversity is hidden or is masked by the averaging process. So this is about average, which is the measure of the size of your data. Yeah. When you have 2 numbers, the average is halfway between the 2 numbers. And if you add bigger numbers to your bunch of numbers, then the average moves up. If you add the smaller numbers, your average basically moves down. So the average is always lying somewhere between the smallest and the biggest number on your list. Okay, take 5 and 7 for example. The average obviously is the middle point, which is 6 in this case. How you calculate it, you don't have to even calculate, because you know between 5 and 7 falls number 6. But to be mathematically clear, so you add 5 to 7, then you have 12, then you divide by the number of the entities that you are taking the average of, which is 2. So 12 divided by 2, you have 6. That's your average. So if you add now 9 to your list, then you have 3 numbers, 5, 7, and 9. And then the average of these 3 numbers, if you do the math, it's 7. And you can see by adding a bigger number to your data, your average has moved up. Okay, and that's how the averaging process works. Now back to the question that we started with. Okay, yes, so we found out that each month the Office of Labor Statistics calculates the average hourly earnings from the payroll data, and then they figured that the total wages paid out, and then they find out that during the recessions, the average hourly earnings goes up, and then when the recession ends, the average hourly earnings starts going down. How is it possible? How is it possible that the average earnings rise when the economy shrinks? How we make sense of this? So what happens here is that during the recession, if you look closely at your data, you will find out that during the recession, companies tend to lay off workers with the lowest seniority, who are also the lowest paid employees. And this results the average wage of those left on the payroll going up. Okay, so when the recession happens, the companies lay off low-earning employees, and what happens? You have a bunch of data coming from those left already in the company who are earning more, and then that's how your average looks bigger during the recession. And then when the recession ends, low-paid workers are hired again, and then this causes the average wage going down after the recession. And the lesson, the conclusion is that it really matters who is included in your average and who is excluded in your averaging process. Now let's look at how the average and histogram are related. Let's begin with an example here. You see on the picture, this is the graph, this is the histogram for the weights of 7,000 women. Okay, this is how the weights measurements are distributed for your 7,000 sample of women. And what you find is that the average of these weights out of 7,000 women is 66.2 kilogram, and this is marked with a dashed line on the histogram. Well, you might guess that, okay, when the average is 66.2, then you might guess 50% of the women are above the average in weight and 50% are below the average. But this is not correct. When you do look closely and you measure the area under your histogram, you will find that only 41% are actually above the average and 59% are below the average. So what's going on here? So let's clarify this with some examples. Okay, so assume you have a list of numbers 1, 2, 2, 3. This is the histogram for your 4 numbers. You can see 25% of your numbers, which is 1 out of 4. Then you have your 2, which are making 50% of your numbers. Okay, you have 4 numbers in total, 2 of them are 2, and then you have 3, which is only 1 number, and it makes 25% of your data. Okay, and so the average is also marked with an arrow in the center, which is 2. You also see that the histogram is symmetrical at number 2, and then number 2 is also the average of your data. Okay, if you do the math, simply 1 plus 2 plus 2 plus 3, that's 8 divided by 4. There are 4 numbers, and then you have 2. Okay. So this is the center point. Average falls in the center. The histogram is symmetrical, and half the area under the histogram lies to the left of your average, and the other half falls to the right of your average, in this case, in this example. Right? Now look at the histogram for the same list, only replace number 3 with number 7. What happens here is that the bar over your 3 now shifts to the right, and it goes above number 7. And now you have broken the symmetry of your histogram. So what's the average for this new list? Obviously it's 3 if you do the math. Okay, you have 1, 2 is 3, add 2 it's 5, plus 7 which is 12, divided by 4 is 3. So the average is also marked, also on the histogram. You see the average now shifts to the right compared to your first list, compared to the histogram above. You see the average has moved to the right. So what we see here is that it really helps to imagine a histogram like a seesaw. Okay, then you can see the histogram is balanced at the average point. A small area which is falling far away from the average can balance a large area closer to the average. Just like a small child sits farther away from the center of the seesaw to balance a large child sitting closer to the center. So blocks in a histogram work the same way. This explains why percents of cases on either sides of the average can differ from 50%. For your second list, 1, 2, 2, 7. So if you want to guess without calculation where is your average, you might say, okay, I will find the point that divides the area of the histogram by half, and that's for both cases is number 2. Okay, number 2, if you split your histogram at number 2, you will see you will have 50% of area on the left and 50% on the right. But that's not the point that balances like a seesaw. If you imagine your histogram like a seesaw, and you center your seesaw at number 2, you can imagine that because the right sides of the blocks in your histogram are spread farther away, then your histogram is not balanced. It will go down on the right side, because even though the weights are the same on both sides, but on the right side they are falling farther away from your center point, and that's why your histogram is not balanced. So how do you balance it? You basically imagine the average is where the histogram should be centered in order to make it balanced. So the center point can't be at 2 for the lower histogram. It should be somewhere to the right, so that the histogram is centered, is balanced like a seesaw. Okay, so here's the rule. The average point is the balancing point for a histogram, like the center of a seesaw. So the average is not about having equal areas on either sides of the average point. If histogram is symmetric, the average is also where it splits the two sides by equal areas, but generally the average is where the areas being balanced on either side. So a smaller area spreads farther away, and that gives the same weight as the large area closer to the average. That's something important to remember. Now here is the time to introduce the idea of the median. Okay, so median of a histogram is also another way to describe the center of a histogram, and it's the value with half the area to the left and half to the right. So imagine these two histograms. The median is 2, because that's the value that divides the histogram by 50-50 to the left and right. And but for the second histogram, because the area to the right of the median is far away compared to the area to the left, so if you try to balance the histogram at the median, it would tip to the right side. Okay, so the average is somewhere to the right of the median. It is generally true whenever you have a histogram with a long right-hand tail. This is what happens for asymmetric histograms. The histogram that is not symmetric, the average is falling to the side with a longer tail. So in the picture, for example, you have the tails of a histogram. You have three typical histograms. So if you want to look at the median versus the average, you see that the long is the long right-hand tail. In the center you have a symmetric histogram, and in the right you have a long left-hand tail. So for the first one, the average is bigger than the median we showed in this example. For the second one is symmetric, the average and the median are the same. And for the one in the right is the long left-hand tailed histogram. The average is smaller than the histogram. It's falling to the left of the median. So remember, when we deal with long-tailed distributions in statistics, we tend to use the median rather than the average, because the average may pay too much attention, too much focus to the extreme tails of the distribution, and you don't want that, right? This is what happened with your friends in the bar, and Elon Musk walking into the bar, and yeah. So when dealing with the long-tailed distributions in statistic, we talk about the median rather than the average. Now let's have a case study. We have 3 histograms here. The average for these 3 histograms, we have to guess, is around what? And also the median is it equal to the average, or is it to the left of the average or to the right? So for the first one, okay, the average is where? It's simple. The average is 50, okay, because it's the center point, the histogram is symmetric, and the average is 50. The second one, histogram B, the average is 25, okay. You have the range 0 to 50, the average is center. So here is also the median, because it's symmetric, equals to the average for the case B. And for the case C, you can guess the average is around, I would say 40, because you find the point, the areas are split by 50-50, where is the half point in your histogram that divides your histogram to equal halves. And then because on the right side you will have a distribution that falls further away from that point, then the average should be moved to the right of that middle point. Okay, so I would say in this case the median, the average is around 40, and the median is somewhere to the left of the average. Okay, now let's talk about standard deviation. Right, so far we were looking at the center of a histogram as a way to summarize our data, right? Now, the other main parameter in statistics that we face a lot is the standard deviation. It is often helpful to think how a list of numbers spread out around the average. And this spread is usually measured by a quantity called the standard deviation. The standard deviation is used to measure the spread of a data set, okay? And how we indicate a measure of size for some data? Let's begin with a simple list of numbers. So you have 5 numbers like 0, 5, minus 8, 7, minus 3. How big are these 5 numbers if you want to put a number on it? So one way would be like the average. You would say, yeah, I can take the average, and that would give an estimation of the size. And in this case, the average is 0.2. But in this case, this is a poor measure of the size because it only reflects the positives, mostly cancel out the negatives, and it's almost 0. It doesn't really reflect the size of your numbers. How to fix this problem? One way would be to ignore the signs of the numbers and take the average of absolute values, okay? But in statistics, there is another way. You can do something else, and we use the RMS operation, the root mean square operation. The phrase root mean square says how you do the math, actually, but only backwards. So square, you first square all the numbers, then you take the average or mean of the squares, and then you take the square root of the mean, and that gives you the RMS size of your data, your numbers. Okay, so remember the RMS size is the square root of average of your numbers squared. So let's get back to our simple list again. So if you take the average by ignoring the signs, only the absolute values, you get 4.6. And if you now take the RMS size, so square all the numbers and then average them out and then take the square root, the result would be 5.4. So as a measure of the overall size of these 5 numbers, you could either choose 4.6 or 5.4, but in statistics, the RMS size is often used because, as you will see in future episodes, it better fits with the algebra that is very common in statistics. Okay. Now let's look at another example. What is the RMS size of this list? 7, 7, 7, 7, 7, 5 sevens. Okay. So remember, the RMS is a measure of the overall size of your data. And in this case, in this example, all the numbers equal to 7. So how you communicate, how you put an estimate on the size of your data set when all of them are 7, it's easy. You don't even have to calculate. It's 7. It's the RMS size of this list of numbers. They all equal. If you take the average, you get the 7. If you get the RMS, you will get the 7. But if you remember the definition of the RMS, it's a measure of the size. If you want to put a number on the bigness, on how large your numbers in the list are, then you use the RMS. And when they are all equal, it's easy. It's 7. Do the math and you will get the 7. How about the other one? So 7 minus 7 minus 7, 7 minus 7. What is the RMS size? How big are the numbers? If you have to put a number, if you give a number on how large they are, again, you are talking about the absolute size of the numbers, not the signs, and the result is 7 again. For both lists, the RMS size is 7. So this was about the RMS. What about the standard deviation now? So getting back to the definition, the standard deviation is a measure of spread around the average. It actually measures the size of deviations from the average. It's a source of an average deviation. So you want to put a number on how big is the spread of the numbers around the average. And then you remember how you put a number on the size of a list of numbers. In this case, on the size of the deviations, you do the RMS. Yeah, so standard deviation is the measure of the size of deviations from the average. So one thing to remember, as a rule, we see most entries in statistics, in data, will be around 1 standard deviation away from the average, and very few will be more than 2 or 3 standard deviations away. This is very important, as you can see in the sketch. Remember these 2 sketches. So we talk about 68% and 95% rule. So for most data sets, 68%, that is 2 in 3 of numbers of data, are within 1 standard deviations of the average, and the other 32% are farther away. Also, 95% rule says that 95%, that is 19 in 20 of numbers of your entries, fall within 2 standard deviations from the average, and the other 5% are farther away from the average. And also remember that this rule applies to many data sets and lists, but not to all of the lists, as we will see in future episodes. So how do we calculate the standard deviation? Easy, if you remember the definition. So we need to find out the deviations from the average and then take the RMS of those deviations. Then you have your standard deviation, which will tell you how far away your numbers are from their average. For example, again, this is another example. You have this list of numbers, 13, 13, 13, 6. All of them are 13. What is the RMS size? So without doing any math, you remember the RMS is a measure of the size. So when all of them are equal, if you want to put a label on them as to show how big they are, you put the RMS size, you put 13, because all of them are equal. You don't have to even do the math. What is the standard deviation? And the standard deviation is the measure of deviations from the average. So for this case, all of them equal to 13. Obviously, the average is also 13. So the other numbers, how far away they are from the average, they are exactly the same. So there is no deviation. All the deviations from the average is 0. So for that reason, for this list of numbers, for this data set, the standard deviation, the measure of deviations from the average, is 0, because there is no deviation from the average. Another example, let's look at these numbers, 20, 10, 15, 15. So the first step, we want to do the standard deviation. We first need to find out the deviations, right? So what are the deviations? So to find the deviations, we need to figure out the average first. So if you do the math for the average is 15. And then the second step is to find the deviations from the average one by one. So if the average is 15, so deviations for the first is 20 minus 15, 5, 10 minus 15, minus 5, 15 minus 15, 0, 15 minus 15, 0. The deviations from the average, okay? And the next step is to find the size. If you have to put one number on the size of these deviations, what would you do? In statistics, we do the RMS. And the RMS is you first square all the numbers, then you take the average of those squares, and then you take the square root. And if you do the math, you get to roughly 3.5 for this list of numbers. So that was the manual way. In Excel or Google Sheet program, you can take the list of numbers. You can do the average manually in the spreadsheet. And then you can also use the built-in functions for the average and also for standard deviation. And let's do that. Okay, so The numbers are here. The average is the sum of the entries divided by the number of entries. Yeah, if you want to do the average manually, step by step, this is how you would do it. Or you can use the average function. So use the function and then you select the list. This returns the average of the numbers. Now you want to find out the deviations. So you one by one for each number, for each cell, you deduct it. You subtract from the average each of the data, and that is your deviation, the list of deviations. Now you want to find out the RMS of these deviations. How you do the RMS of these deviations? You first square them. You then take the average of these squares. And then you take the square root of the average of deviations. That will be your standard deviation. Alternatively, if you want to use the function, you have to use the standard deviation for the population, and it will return your standard deviation for this list of numbers. Okay, note that standard deviation is in the same unit as your data, because squaring first, then taking the square root returns you basically to the original unit. Also note that you should not confuse the standard deviation of the list with its RMS size. Now moving on, let's look at a more practical case. So you have gathered the heights of 7,000 people. The average height is 161.6 centimeter and the standard deviation is 6. So what does this data mean? How you can interpret this? The average tells us that most of the people in our population are somewhere around 161 centimeter tall. Okay, but because we have standard deviation, we know that there are also some deviations from the average, and this is given by the standard deviation. So some people are taller than the average, some are shorter, but how big are these deviations? This is what standard deviation is trying to tell us. You know, that standard deviation, remember, it indicates the size of deviations from the average, and in statistics, how we give a measure of the size, we use the RMS operation. So the standard deviation is the RMS of the deviations from the average. So let's look at the height histogram of these 7,000 people. In this figure, you can see the average is marked with a vertical line. So the zone within one standard deviation on both sides of the average is shaded. One standard deviation to the right, one standard deviation to the left. So this zone shows the people who differed from the average height by one or less standard deviation. Okay, either more or less than the average. And this area also is about, if you measure the area under the bars under the histogram for this zone, it's about 67%. So you can say that about 67% of the people deviated from the average height by one standard deviation, which is in this case 0 to 6 centimeter from the average. Now let's look at the same histogram. This time the zone within 2 standard deviation of the average is shaded. So the shaded area represents people who differed from the average height by 2 standard deviation or less. And if you measure the area, you will find that it's about 94%. So you say that about 94% of the people differed from the average height by 2 standard deviations or less. And that is 12 centimeter or less. Remember, your standard deviation is given, and that's 6 centimeters. So you can say that about 94% of the people are different from the average height by 2 standard deviation or less. So you have an estimation of where are your population falling around the average in this way. Also, otherwise, in another terms, you can also say that very few people deviate from the average height by more than 12 centimeter. As you can see, there is only 5%, a very small area, a small number of population people deviate from the average by more than 12 centimeters. That's also another way of putting it. So to summarize, about 67% of people differed from the average by 1 standard deviation or less, and about 94% differed from the average by 2 standard deviations or less. Actually, when you look at the data, you will find that in this case, in this example, only 1 person in 7,000 people was taller than 4 standard deviations from the average. So for this data set, we can say that the 68-95% rule works quite well. So where do these numbers 68 and 95% come from, you might ask? Stay tuned for the answer in the next episodes. Now let's look at some case studies. So for this case, we have the average height for boys given for the boys aged 11, and the average height is 146 centimeter with a standard deviation of 8. And we pick one boy, we look at one data point for one boy, and it is 170 centimeters tall. So the question is how you describe this in terms of standard deviation. He is above average by how many standard deviations? That's easy, right? So he's above average by 24 centimeters, and 24 centimeters is how many standard deviation? Is 8. So 24 divided by 8, it's 3 standard deviations above the average. Next case study. How would you describe these 4 numbers? You know, given the average height for the boys in the previous example, which is 146, and the standard deviation of 8. So how would you describe these four guys, each of them with a given height, 150 centimeter tall, 130, 165, 140? How would you describe this? So 150 is 4 centimeter above the average, and it's half standard deviation. So you would describe this about average. Yeah, it's very close to the average. How about this one, 130? How many standard deviation it is lower? It is 16 centimeter lower than the average, and 16 centimeter is 2 standard deviation, and 2 standard deviation is at the very extreme, you know. So remember, 5% of the data fall more than 2 standard deviation or above or below the average, and so you describe this height as unusually short. How about 167? It is 19 centimeter above the average, and 19 centimeter is more than 2 standard deviations away, and 2 standard deviation away is unusually tall. Yeah, it falls under the category of very rarely tall people. 140 is only 6 centimeter below the average. 6 centimeter is less than 1 standard deviation, so you would describe it as about average. The next question is about what percentage of boys were between 138 and 154, and about how many, what percentage of boys were between 130 and 162 centimeter. So let's look at these numbers in terms of standard deviation. So 138 is how many centimeters? It's 8 centimeter below the average. Okay, and it's 8 centimeter is 1 standard deviation. So this range is when you convert it to the average and the standard deviation terms, so it's the average plus minus 8 plus minus 1 standard deviation. So using the 68%, 95% rule, you remember that the data, 68% of the data fall within 1 standard deviation. So this is the answer. So approximately 68% of the boys have heights in this range. This range, again, you convert it to the terms of the average and the standard deviation, and then you will find that this range is basically 2 standard deviation, 16 centimeter on 2 sides of the average. So this range is basically average plus minus 2 standard deviation. So then using the 95% rule, approximately 95% of the boys have heights in this range. Next case study, we have 3 lists of numbers. Each has an average of 50. And the question is, which one has the biggest spread of numbers around the average and which one has the smallest? Okay, so we know the average. Then let's look closer. So the average is 15. We have 0, 20, 40, 50, 60, 80, 100. So the range of all 3 lists is the same, minimum 0, maximum 100. The first one is almost equally spread, 20, 40, 50. And the second one, you have the same minimum and maximum, but they are mostly clustered near the center. The last one, you can see 0, 1, 2, then 50, the average, and then 98 jumps to the higher end, the last 3 numbers. So if you put it on a sketch, visually you can see that the highest spread around the average is for the last list of numbers, as you can see, right? You can see, yeah, the minimum and maximum is the same for all, but for the third list, you can see that the numbers, more numbers are falling farther away from the average. And which one has the smallest spread? You can say this one, yeah, because again the minimum and maximum is the same, but 5 of the numbers are very closely clustered around the average. So if you do the calculation, if you do the math, you will see that this one has the smallest spread around the average. More of the numbers are closer to 50. So that gives you the smallest spread. Remember, do not confuse a spread with the range. There is more to spread than just the range. So for this case study, the range is same for all the data sets, but the spread is different. Now let's move on to the next case study. So the following lists are given. So the average, again, we know is 50. We should guess the standard deviation. Is it around 1, around 2, or 10? Without doing the math. How would we do that? Let's look at the numbers. We have the average. So 49, 51, 49. So you can see it's jumping 1 up and down around the average. So how we can guess the standard deviation? Standard deviation is the size of deviations. So if we want to guess the size of deviation, is it 1, 2, or 10? We should go for 1, yeah, without doing the math. Second one, 48, 52, 48, 52, 48. See, it's jumping up and down 2 by 2 within the from the average. So that's the deviation from the average. The size is 2, so that's your standard deviation. So we would guess 2. That's the standard deviation for this, without doing any math. Third one, 48, it's 2 under the average, 51, 1 above the average, 1 below, 2, 3, 2, 4, 1, 3, 1. Yeah, it's not equally equally spread, but if I had to guess, I would guess 2 without any math, because we have 2, we have 1, few of them are 3 up and down the average. So on average, if we had to put a number on the size of the deviation, on the standard deviation, then I would go for 2. The last one, 60, that's 10 above the average. 36, that's 14 below the average. The 31, that's almost 20 below the average. So if we had to choose between these 3 numbers, I would choose 10 as a guess for the standard deviation. Okay, remember the standard deviation says how far entries are from the average overall, as a whole. Next, so in this case study, we have 2 researchers, researcher A and B. Researcher A takes a sample of 100 men at a given range in a town, and researcher B takes a sample of 1,000 of such men. So the question is, which one will get a large average for the height, and which one will get a bigger standard deviation for the heights? Okay. And also we have to guess which is more likely to observe the tallest height in their sample, and which one is more likely to observe the shortest height in their sample. So this is a very interesting question. So we are getting close to how to use the average and standard deviation and how it relates to the sample size. So the short answer is that because we are dealing with the same population and we are taking samples, of different size from the same population, you expect that the average and standard deviations to be almost the same for both researcher A and researcher B. Okay, and also, the standard deviation you expect to be about the same for both researchers, not necessarily equal, but about the same, because they are taken from the same population. Next question is, which is more likely to observe the tallest height in your sample? So the bigger the sample is, if you imagine you have 1,000 for researcher B, so the bigger your sample is, the bigger the range is, right? So when your range is bigger, then it's more likely to see the tallest or the biggest numbers or smallest number, because you have a bigger range, you have a chance of having a bigger range. Again, remember the standard deviation and the range measure different things. Case study number 6. So in a survey with a sample of 7,000 men, the average height of the men is known, and it is 175 centimeter. And the standard deviation is also known, it is given 8 centimeter. So tomorrow you want to select one man randomly from this population. Okay, so then you have to guess his height. What would be your best guess for the height of your randomly selected man? What value would you choose? And then how accurate do you expect your guess to be? These are typical statistical questions that we will face in the real world in application. So the answer is that your best guess is to go for the average. It's your best guess would be to go for the average. And then if you want to put an estimate how accurate your guess is, you would say that, for example, there is about 1/3 of a chance to be off by more than one standard deviation. Remember the 68% rule and 32% rule. So that's how you put number on your guess and on the accuracy, of your guess. The next question is, then you select a new series of men randomly and compare each height with your guess to see how far off your guess was. How would you do that? You want to understand what is the RMS size of these numbers, these amounts off from the average. So the average, the standard deviation. You select a new series of men out of these 1,000 people, randomly, and then you compare each height, you measure the height of them, and then you measure each height with your guess, which was the average. Yeah, you guess the height to be 175, and then yeah, you select a couple of people, and then you measure their height, and then you want to compare each height with your guess to see how far off your guess was. So the question is, what is the RMS size of these amounts of? So actually we are asking about the standard deviation, because the standard deviation is the RMS of deviations from the average. So basically it's asking about the standard deviation. Standard deviation is already given, which is 8 centimeters. So you expect that the RMS size of these deviations from your guess would be 8, as given by the standard deviation. Next question, let's see what we have. So we have a list of numbers. We have 3 lists here. We want to calculate the average, the deviations from the average, and standard deviation. Yeah, let's do it. So for first list, if you do the math, the middle number is 4. The deviations 1 by 1, so you subtract 1 minus 4 is minus 3, 3 minus 4 is minus 1, 4 minus 4 is 0, 5 minus 4 is 1, 7 minus 4 is 3. This is your deviation from the average, and the standard deviation is the RMS size of the deviations. If you do the math, you get 2. You can do it in Excel or in the Google Sheet, as we saw how to use the functions. You will get 2 for the standard deviation of this list. For the second one, if you do the math, you sum them up, you divide them by 1, 2, 3, 4, 5 by 4, you will get 9. Then the deviations from the average, so 1 by 1, 6. How far away is from 9? Minus 3. 6 minus 9 minus 3. 8, how far away it is from the average? Minus 1. Minus 1. 9 is 0, the deviation is 0. 10 is plus 1. 12 is plus 3. So the RMS size of the deviations from the average, if you do the math, you square each of them, you take the average of all the squares, and then you take the square root. The answer is the standard deviation. Again, it's 2. Next list of numbers, 3, 9, 12, 15, 21. If you do the math, the average is 12. You sum them up, you divide by 5. The deviations, again, 1 by 1. You do the math, 3 minus 12, it's minus 9. 9 minus 12 is minus 3, etc. So you get the deviations, and the standard deviation is, what is the RMS size of the deviation? You do the math, you get 6. So there is a clue, there is a hint here. If you pay closer attention to these 2 lists, you will see that list number 2, the second list, is made by adding 5 to each number in the first list. So 1 plus 5, 3 plus 5, 8, 4 plus 5, 9, 5 plus 5, 10, 7 plus 5, 12. So what happens when we add a fixed number to all the numbers in our data? We will see the same amount of numbers is added to the average. So if we add 5 to all the data points, your average is also increased by 5. So you can see 4 plus 5, 9. But no change you will see in your deviation and your standard deviation. Okay, so this is the carryover rules. So adding to all the entries in your list of data carries over only to the average. Yeah, this is the important rule. And if you now pay closer attention to the last list, you will see that it is made by multiplying each entry by 3. So 1 multiplied by 3 is 3, 3 times 3 is 9, 4 times 3 is 12, 5 times 3 is 15, 7 times 3 is 21. So you can see it's made by multiplying each entry by a fixed number. So what happens to the average, to the deviations from the average, and to the standard deviation? You can see the average is also multiplied by the same number, by 3 in this case. So 4 times 3 is 12. What happens to the deviations from the average? You can see it's the same. So each deviation is multiplied by same number, by 3, and also for the standard deviation, it is also multiplied by 3. So we can say that multiply operation is carried over to the average, to the deviations from the average, and to the standard deviation. So remember this. And last case study, imagine your company gives all the employees a flat monthly raise of A, $700, B, 5%. So what will be the effect on the average monthly salary of employees and to the SD? So this is the carryover rule. So if all your colleagues get the same amount of raise in their salaries, $700 in this case, so the average also goes up by the same amount, okay, by $700, but the standard deviation will remain the same. So case B, if all the employees get a flat raise of 5%, so this is multiplied, means your current salary is multiplied by 1.05, yeah, your new salary, and for all other people is multiplied by the same number. So this is the carryover rule for the multiplication. What happens to your for the average to the overall salaries of the whole employees? Yes, the average is increased by 5%. How about the standard deviation? The standard deviation of the salaries will also be increased by the same amount, by 5%. So as a summary of this episode, what we learned today. So we learned that a typical list of numbers can be summarized by its average and standard deviation. We learned that the average locates the center of the histogram, meaning the histogram is balanced with support at the average, okay? And we learned that the half area under the histogram lies to the left of the median and the other half falls to the right of the median, and the median is another way to locate the center of a histogram. The RMS size of a list of numbers measures how big the entries are in absolute terms without considering their signs. We learned that standard deviation measures the distance from the average. It's a measure of the average size for the amounts of the average. It's the RMS size of deviations from the average. That's the standard deviation. We also learned an important rule, and which says roughly 68% of the entries on a list of numbers are within one standard deviations of the average, and about 95% are within two standard deviations of the average. And we learned that this is true for many lists, but not all. With these tools, we can transform raw data into useful insights in statistics. These tools basically help us to understand the patterns, the distribution, and scale of our numbers. So next time someone quotes an average, you will know to ask, what about the spread? Who is included? And is the median telling a different story?